delighted to have today in the math department Professor Neil Siegel, who is our math department's most distinguished alumni. And one reason for that is in 2023, he received the National Medal of Technology from President Biden. These national medals are very, very distinguished and very, very exclusive. So we're delighted to have, as one of our alumni, a national medal winner. Well, not only is he a national medal winner, he's fellow of all the societies with many prizes and other things, maybe too many to mention. Neil was, as we say, a student in our department in 1974. At the age of 17, he came to us he came to USC. None of us were around here except for Susan Montgomery. We need to keep that open.
Oh, open? Okay.
Yeah. And then went on to get a master's degree in 1976. Then he went to work, real work, work as an engineer. And he began work in TRW, which later became Northrop Grumman, and rose to the very top of these engineering company. And he, among other things, he led teams creating new products with the general theme of automation to support decision makers in complex and stressful environments. And there are a lot of complex and stressful environments, as we all know. And in particular, he has important applications to military and civilian applications to his name. And then he retired to become a professor again, or again at USC. So in 2016, he returned to USC as the IBM Professor of Engineering. And we are very happy to have him on campus teaching and working and consulting and doing the sort of things that an engineer does in retirement. So Neil will speak to us a theory of development for complex engineered systems. Thank you very much.
It's very fun to be here. As was mentioned, I came here in 1971 as a 17-year-old freshman. My second semester, I took a class. I was still 17 with Dr. Montgomery. Took a class from her as a graduate student too. So it's amazing to see you still here, and it's amazing to be here after all this time. That is more than 50 years. It's hard to believe. Anyway, I always felt very well prepared by the math department to go off and do other things. I was always an intensely hands-on and practical person. I was never cut out to be a theoretical mathematician. But I had a lot of fun in the math department. But I had a wonderful time in my career. I went to work because I got tired of being a starving student and I wanted to get married. And I kind of BS'd my way into a programming job. I had no qualifications, but my wife is a brilliant linguist and she says, 40 verbs, 100% regular grammar, how hard can programming be? She speaks 10 languages, so I can't do that. Anyway, and there I discovered a field called systems engineering and fell in love with it. It became my life's work. And many, many years later, I came back to the engineering school here, did a PhD. And then the dean of engineering had been after me for years and years. Whenever you're ready to retire, come teach. Whenever you're ready. So finally I did it. Anyway, so I'm glad to be here, and I'm glad to be here in the math department. It's very fun. So I'm going to talk. About engineering, but there's a theoretical bent, and there's a lot of math concepts that inform what I do. Susan already mentioned the things that, as I said, the main thing today is I'm actually an alumni of the department, which is kind of fun. I like to think of as engineering and all the things like science and math and support engineering as being really important for the world, right? You look at things like this, right? They doubled human life expectancy, right? So what the archaeologists tell us is that for 500,000 years, human beings lived between 30 and 35 years. Some people, like the Bible says, right, for 70 or maybe 80 years, right? But most, because of the very, very high infant mortality rates, the average was between 30 and 35 years. And then, if you look at my textbook, there's actually a graph, about 150 years ago, it started going up. And for the whole world, it's about 70 now. And of course, in the United States and Western Europe, it's quite a bit higher. And somebody is going to go figure out what happened. You stop the average person on the street and they'll say, oh, it's medicine. And that's not true. It's this stuff, which is really civil engineering, right? And it's especially the first two items, water treatment and sewage treatment, right? Because the thing that was killing lots and lots of young and middle-aged people was dysentery and typhus and stuff like that. So that these things, but the food preservation, food transportation is really big too, right? But these things are about 80%. You can see that. My wife ran a non-government organization in rural eastern Tajikistan for about 10 years. So they have almost no modern medicine, but they have water treatment, sewage treatment, and people live into their late 60s, right? So you get a lot of this benefit without any modern medicine. And these are kind of old examples, but of course we could talk about new examples, just in time and the internet and supply chains and police and ambulance dispatch and engineering. These complex engineering projects are really a big deal for the world, right? And like I said, they sit on top of science and they sit on top of mathematics and they sit on top of lots of other things. There's a lot of art involved in building these things too, right? Which is what makes them so fun. And I've been involved, by the way, in all of these kinds of things, not just aerospace and defense. Big company does lots of stuff. So, it's not just civil engineering, kind of little Bruce, which is old stuff. It's this new stuff too. So we keep doing this, right? So these big engineering projects, these complex engineering projects are really important for the world. I mean, literally, 100 years ago, the population of the planet was 1 billion people, and today it's 7.5. Right? Those 6.5 billion people are literally being kept alive by the continued operation of all these things, right? And our life gets better because of these things, right? I mean, to be blunt, we all live better than any king or queen did 100 or 200 years ago, right? Heating, air conditioning, anesthesia, right? Dentistry, you name it, right? We have it so good, it's unbelievable. Sewer systems. The dirty secret is that you might say that after thousands of years of doing this stuff, we ought to know how to do it. And the dirty secret is actually we don't, right? That a vast majority of these kinds of engineering projects fail. Some people actually have collect data and say that 85% of these complex engineering projects fail, meaning that they get stopped before they're done. They're over budget, they're behind schedule, or they're not looking like they're going to meet their technical goals. And so the funding customer loses interest, right? That's what I mean by a failure. Some people say it's not that bad, it's only 60%. But whatever it is, it's a lot, right? And that represents unbelievable opportunity cost for both skilled people and money, right? So this is a big deal, you would think, right? And these are the things, and it's the obvious things, but it's also sometimes these things have unbelievable, unintended adverse consequences, right? That make people say, we can't continue this. And the other thing is sometimes the intended users just don't like it. You can build a system, it can meet all of its requirements, you think you are perfect, and the users hate it. I've seen that too, right? Bruce has seen that too. Bruce is my colleague in the ISE department, but more importantly, 30 years ago, he was my colleague in the aerospace industry. Different life. So I'm going to assert to you today that it's important to understand why these projects fail, why so many of them fail. And I'm further going to assert to you that the general view in the literature of why they fail is completely wrong, And I'm going to tell you why. I'm going to tell you what I think instead is the correct cause and try to show you why. Okay. But of course, if our analysis of the root cause is wrong, then therefore we will take the wrong corrective actions and nothing will get better. And since the failure rate is still really high, that's probably what's going on. So I like to talk about this thing called the systems method. I think the term is due to a guy named Dr. Simon Raybaum, who was the R in TRW, the father of the United States Ballistic Missile System, and had an affiliation with USC in the latter part of his life. He died at 103 just a few years ago. His wife, Virginia, was on the board of governors of the university for 30 years or something like that. And it's natural for us to think about parts, right? So when we buy a car, do we want a 6-cylinder engine or a 4-cylinder engine? I'm old, right? So do we want a manual transmission or automatic? Try and buy a manual transmission these days. It's not so hard, right? Not so easy, right? Tires, right? There's options. So we think about parts because we can grasp them and we can grasp their function. But actually, the parts are not always of the essence of what we're going after, right? Really, we build systems to obtain something more than what the parts do. There's a guy I used to teach here named Everhard Rechten, Dr. Rechten, who was the president of the Aerospace Corporation, and he called this 1 + 1 = 3 effect emergent behavior. And that we design these complex societal systems to get some kind of emergent behavior, right? You do water treatment and sewage treatment and you double human life. Right? When you started thinking about water treatment, people started thinking about water treatment and sewage treatment really long before Pasteur or anybody else invented bacterial theory, right? They had no idea that they were going to double human life, which by the way had adverse effects, right? The population increase and the problems of food and all that implied and stuff like that. But what we're talking about is this business of the whole is greater than the sum of the parts. The example I really like to talk about is the thermodynamic efficiency of a child's wagon, which is a very sophisticated phrase to describe a fairly simple thing, right? So when I was about 6, I had a little wagon, right? So it's a box, right? An open top metal box with a handle and 4 little wheels and 2 really primitive axles, no wheel bearings, right? No, nothing, right? But I could put much more in that cart and pull it down the sidewalk than I could lift in my arms, right? It turns out that a child's cart is just about the second most thermodynamically efficient device that has ever been created by human beings. A bicycle is probably, because it has large wheels, is more efficient. But there's nothing in the parts that is particularly good. Right? Like I said, my wagon, I was poor, right? My wagon didn't even have bearings, right? It was just, the metal rod going through a round hole in the metal, right? But it's still got pretty good thermodynamic efficiency, right? And to spend a lot of money on bearings or wheels probably would have been wasted. It's like my Toyota Camry, probably with a tailwind can't go faster than about 80 miles an hour. So it would be stupid for me to buy tires that are rated for 160 miles an hour, right? It's not about the parts, but it's how the parts are assembled. It's the architecture of the child's wagon, right? If you put it together in a different way with the wheels on the top, right, you would have a sledge and not a cart, and you would have missed most of the potential thermodynamic efficiency, even though it's exactly the same parts. Right? And so this is the systems method, is thinking not about parts, but about the desired emergent behavior. How do you strategize to put things together, perhaps even with ordinary parts, right, to get the desired emergent behavior? Got it? Questions, comments, rejections, arguments? Right? A sophisticated audience, we can take all of that. And in fact, we almost always build these expensive societal systems to get some kind of particular emergent behavior. This is really our hidden goal. And that's why Dr. Ringo and Dr. Rechten, I think, made such a vital contribution to the thinking, because they were the ones that really brought this to the fore. I heard Dr. Rechten talk about emergent behavior back in the late 70s or early 80s when he was still the president of the Aerospace Corporation, long before you could find any reference to it in the literature, right? Long before when he retired and came here, he wrote his own textbook, but that was even 10 or 15 years later. But if you think of the complex societal systems that we're building today or have built recently, the healthcare system, the internet, the power grid, it's the same kind of thing, right? We're aiming for some kind of emergent behavior, right? The power grid is about reliability, right? In the presence of failure, we can still get power to your house, right? If we have one generator serving your neighborhood, when that generator inevitably needed maintenance, power would be off for a while. But now we have a bunch of switches, and we can take this generator and bring power to your house. And if we're smart and good, you won't even notice, right? Or sometimes the lights. But that behavior comes from the way the parts are put together and not inherent in any of the parts, right? And so we need to consider more than the parts in design. This is what we consider the system as a whole. And so Dr. Ramo, I believe, was the one who coined this term system engineering. Okay, so the system as a whole, what do I mean by that? We have to plan the emergent behavior we want. It is, however, a pesky fact that whenever you have something that has dynamic behavior, you're going to get unintended dynamic behavior too, right? So that you got an old-fashioned mechanical clock and the gears, this gear interacts with this gear and this gear, but there's vibration, right? There's going to be unplanned adverse dynamic behavior. In that case, perhaps not critical, but in other cases, it could be really influential, right? We're used to this in medicine. We talk about side effects. That is unplanned adverse behavior. And sometimes the side effects are so prominent that the drug gets repurposed to take advantage of that side effect. A lot of drugs like that. And there's even some complex engineered systems I could talk about that were built for one purpose. And when the users started testing, they discovered that this system can be used for, there's a very expensive airplane called AWACS, AWACS, people use airborne warning control systems, big Boeing 707 with a radar on the top. It was built for a particular mission. During its formal test program, an Air Force general told me this, they discovered it was good at another mission. And the 40 years since it was built, it has never been used for 1 minute for the original purpose for which it was built, because they liked it so much for this other purpose, right? But we get this unplanned dynamic behavior. So we also have to design to tamp down this unplanned dynamic behavior, both in terms of probability that it will occur, but also in tamping it down in terms of the magnitude of the impact if it does occur, because we can never tamp it down to 0%, right? This is the real world. This is where we leave the beautiful world of mathematics, and we have to deal with the pesky real world where everything has to be expressed probabilistically and nothing is 0 and nothing is 100% except gravity, right? So this gives us 2 goals for the design system. And I like to kind of think that that explicit focus on the second one is my contribution to the theory. And I'm going to talk about that really mostly for the rest of the lecture. But there's, we have to focus on the interaction methods and controls, what I call the control structure, right? So it's very normal to think about the algorithms that accomplish the mission, right? The things that crunch the numbers, that determine what the right dosage of a medicine is, the things that manage the power, right? So that we don't put too much voltage on this part of the power grid and all that kind of a huge problem, by the way, right? Because the load is not under anybody's control, right? The offered load on the power grid is what it is. And the poor grid operators are constantly turning generators on and off, right? To try and match the offered load and switch things around, right? So the controls, rather than the core algorithms, are actually really the hardest part. But that's not what most people think about, right? They think about the algorithms that accomplish my mission. But the control structure is really a hard part. And then, we have the practical aspect of figuring out what all the parts are going to be and making sure that they're available in time, and achieve balance. Like I said, you don't want to spec tires for your Camry that are rated for 160 miles an hour because you're probably spending a lot of money that you don't need to, and so on and so forth. I spent a lot of my career as a government contractor building stuff for the United States federal government. And everybody likes to tease the government about red tape. believe me, there's a lot of red tape. So I always like to, in defense, point out one brilliant insight that is in all that red tape. So there's something called the Federal Acquisition Regulations, which is the book. It used to be a book, now it's a webpage on the internet that says how the federal government buys something. And it says, you may not feel the system, anything that the government buys, you may not put it into operation till you have proven that it is both suitable and effective. Now, in ordinary human discourse, it's not clear that those words mean something different, right? But if you read the Federal Acquisition Regulation, they do mean something. This means it meets its requirements. This means it meets its, I got this back, right? This means it meets its requirements. This means it can be used by the intended people. I had a contract once where right there in the contract, it said the people, for the US Army, the people that are going to use the system can read no higher than the 10th grade level, which I thought was brilliant on the part of the Army to recognize this and to actually tell me that, because otherwise you could build a system that requires a PhD in computer science to operate, right? And that wouldn't be suitable. It might work, right? But it wouldn't be suitable. So these words are different. And so, you know, the one example of useful red tape that I found in my whole career in the federal government is that they recognize that, right? And then early in my career, I probably won't talk about it, early in my career, I was building something for a healthcare application. That turned out to be really important. It saves about 100,000 lives a year in the US alone and will forever, because the thing we built is long obsoleted and out of use, but people are going to build that capability into every system that came after them. So it was kind of a big deal system, right? And we nearly failed. So the first time we built it, we had some doctors we were going to test it with, and we signed up and we let them try it. And they all said two things to us. They said, it works, and I refuse to use it. And it turned out that there were completely social reasons why they were going to refuse to use it. And I was 24 years old and I hadn't thought of that, right? I just never thought of that. And I didn't know what to do about it. But somebody a little older than me, a little wiser and more experienced on the scene said, well, let's sell it to pharmacists instead. Turns out that we were showing the doctors up, right? There's a situation that used to happen, doesn't happen so much anymore, where you're sick, you go to your doctor, she listens to you, she does some tests and she says, oh, you need this medicine. Okay. A week later, you hurt somewhere else. So you go to another doctor and you go through the same thing. She's a good doctor too, but she gives you a different medicine for this other thing. And sometimes those two medicines interact fatally or sometimes just badly, right? 100,000 people a year were dying when we started this in 1981. Every year in the United States alone from that effect. So the first thing we learned is that doctors didn't know. We would go to doctors and say, do you know? And they would say, that can't be true. That's not what we do. Right? Anyway, so we built this thing and the doctor would say, oh, I'm going to give you warfarin. You say, you're doctor number 2. And then you press the button on the computer. We told you to look at the computer first, but you don't. And then it pops up and says, if you give her warfarin, she will die. Don't do that. Give her this other blood thinner instead, right? So doctors didn't like, yes, the information was correct and useful and they followed it, but they hated the idea that it might show them up in front of their patients. That's probably still true, right? I never thought of that when we were building this thing. I never thought of it, but it wasn't going to go anywhere. It wasn't going to save any lives until we fixed that problem, right? Other thing became obsolete. So the other thing was, there you were using a keyboard. Think back to 1982. Who used keyboards in 1982? Secretaries and key punch operators. Keyboards were low status. Using a keyboard was a sign of a low status job. Doctors did not want to use keyboards in front of their patients. That's probably not true anymore, right? It's probably exactly the opposite. Patients expect their doctors to be using computers, but again, I hadn't thought of it all. So we fixed both problems by selling it to pharmacists instead of doctors. Because you can imagine the scenario, you're the pharmacist, right? So you can legally stop a prescription. You have that authority. So you can imagine the following scenario. You call the doctor up and you say, I'm not going to fill your prescription for warfarin because if you give it to her, you'll kill her, right? You can You'll like that, actually. You get a kick out of that, right? So we sold it to the pharmacist and it worked. These social factors are real. Social factors are real, right? And we can think of more recent examples, masks, right? For example. So that's the system method. So what causes those failures? Okay, so what the literature said, the failures are caused by something called problems with the requirements. So we use a life cycle in the engineering business that says you write requirements, what the system is supposed to do and how well it's supposed to do it. We do a design, how it's supposed to do it, and we build it, and then we test it, we train it and deploy it. And we use this life cycle. And what all the literature, you can look, there's thousands of papers and textbooks out there that will say that the reason these systems, complex system engineering developments fails, the requirements are never good enough and they're never stabilized and they're always changing. They even have this crazy phrase called requirements creep. So you might have 10,000 requirements on a big system, and because 5 change every month, you cause the system to cost 10 times as much. So you mathematicians will get this. Most engineers never thought of this, right? That's a highly nonlinear effect, right? So 0.1% of the requirements change and suddenly the thing's 5 years late and it's costing 10 times as much as it's supposed to. That's a very nonlinear effect. And requirements really should be kind of a linear effect, right? It just, I'm implementing 10,000 of these things and they're kind of independent of each other, right? There shouldn't be a complex nonlinear interaction like that. Right, so you see, I learned something in the math department, right? And then something else happened. So early in my career, I kind of accidentally ended up fixing a project that was in trouble, and I got a label put on me saying, Neil is a guy who can fix projects that are in trouble. And I spent the next 7 years of my career being kind of the designated fix-it guy, being sent from one problem program to another. And what I found is they all had good requirements, and what they all had were inadequate designs. And I learned something even wackier. All of the designs were bad in exactly the same way. Exactly the same way. Okay. And, obviously this happened in my mind a lot slower than I'm describing it, right? It was a 20-year process to really kind of get this out. What causes these failures is, think of what I said on that previous slide. We have to design our system to get the emergent behavior we want. But I added that second bullet. That second bullet is what came out of this 7 years of experience. We also have to design to prevent the adverse behavior we don't want. And what I discovered is that's not what engineers are taught to do. They're taught to do only number one and not number two. As a result, I was seeing systems that were 1,000 times slower than they were supposed to be. Not much use, right? They were going to get canceled. That were 10,000 times, I'm not exaggerating, 10,000 times less reliable than they were supposed to be. Not much use. They were going to get canceled. Highly nonlinear effects, right? But now we're not talking about having 3 or 5 more requirements. We're talking about something going crazy inside the control structure. I'm getting ahead of myself here. Something going crazy inside the control structure, which if you think about it, can cause crazy nonlinear effects, right? Think of turbulence. You're pumping water down a pipe and you're pumping 10 gallons a minute and everything's going perfect, and you pump 11 gallons a minute, goes everything perfect, and you pump 12 gallons a minute, suddenly you induce turbulence, and actually suddenly you're getting 1 gallon a minute through the pipe. By the way, the same thing is true of digital communications. The Ethernet works great, usually, as long as the offered load is less than about 40% of the rated signaling rate. Because it works on collisions. It's exactly like turbulence, right? Carrier sense multiple access. What that means is if you want to transmit, you listen, if you don't hear everybody else talking, you start talking, but some percentage of the time somebody else will start talking to you. So you have a collision, and then there's a strategy to correct from that. If the offered load is higher than about 40% of the signaling rate, you get too many collisions, and it's just like turbulence and no data gets through. Okay? That's a highly nonlinear effect. That can explain exactly the kind of wacky things we were seeing. And that led to me, over a much longer period of time, to some insights about design. There's a bunch of stuff that's pretty easy. And there's a bunch of stuff about design that is much, much harder and by and large not taught. Right? So you can pick up a book on software design and you'll see all the stuff in this column and you'll see almost none of the stuff in this column. That's true. Because I've done it. I've read lots of books on software design looking for somebody else who beat me to this punch. Right? So what do? We do something called decomposition. The world air transportation system. We decompose it into airplanes, airports, and air traffic control. We decompose the planes into fuselages and engines and electronics, right? We decompose the engines into, if they're jet engines, into compressors and combustors, right? And so, right? Decomposition. You all get this? This is just set theory in subsets, right? So we teach that, but that's a static analysis, but the critical aspects of our system are dynamic. Those diagrams don't represent dynamic behavior at all, nor do they represent the crosslinks, right? You can't design an airplane without reference to the airport. When Airbus wanted to build the thing they called the 380, the big double-decker jet, right? They discovered that the wingspan they wanted was too big to fit in the alleys at most of the world's airports. And the airplane, when fully loaded, was too heavy for the capacity of most of the runways. And they had to go around to all the airport operators in the world and say, please, 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 if you want my plane, will you please reinforce one of your runways and build some buildings that are a little farther apart so we can get this plane in there. And you know, you may know this, or maybe you don't. LAX has three runways, and they actually went and tore one up and rebuilt it to hold the 380. Took years, right? So they were a two runway airport for several years, but they did it, and so did, you know, Heathrow and a bunch of other airports. They wanted the 380. On that decomposition picture, there is no line that goes horizontally between airplanes and airports, right? So they miss this kind of stuff all the time. Everybody designs to get the dynamic behavior they want, right? You push the button, it causes a switch, we do a calculation, and it opens the sluice gate and water goes down the pipe, right? That's the dynamic behavior we want. But nobody is taught to really focus. If you're building something really important, you've done this. So my company, Bruce's 401k, we were the prime contractor for the Minuteman missile system. Some of you probably know what that is. So 450 big missiles with nuclear warheads on them sitting in silos in South Dakota and other states up there, right? And we used to joke, but it wasn't a joke, 60 years and no accidental launches. Right? But we had a customer that was willing to pay anything to make sure that nothing went wrong. Right? So the connection to the silo, there's three completely independent communication systems, each secure, each highly reliable, each with its own power supply. There's literally a buried steel cable in a metal tube from the command center in Colorado to every one of those 450 silos. Okay, and then there's a radio system and then there's a satellite system, and they are all completely independent. That was not free, right? But it was part of the things that the Air Force was willing to do to make sure that we got to 60 years and no accidental launches. And by the way, if we ever had to launch, it would actually launch, right? You think of NASA and you're always reading, you know, or SpaceX, we had to cancel today's launch, the weather was bad, or there was a leak or whatever, right? So during the time, I've been retired 9 years now, but during the time I was the chief engineer for the company, we would go to 3 or 4 of those silos a year, take the nuclear warhead off, put it in storage, take the missile out, truck it out to Vandenberg Air Force Base here in Central California, put it on a launcher and launch it to a place in the South Pacific. And we went 25 years without a single failure. So we had 450 missiles ready to launch on 40 seconds warning. NASA can't do that. SpaceX can't do that, right? That wasn't free, right? But we had a customer that was willing to spend unlimited money practically on this problem, so that, because obviously if people didn't believe that the system was reliable, it wouldn't constitute deterrence. So why would you do it? By the way, it did seem to constitute deterrence, right? If you go back and you read newspaper headlines from 1948, 1951, They were full of predictions of imminent nuclear World War III between the Soviet Union and the United States, and it never happened, right? If you're a history buff like I am, and you read a lot of history about Europe, there was never a minute in European history of the last 1,000 years where there wasn't a war, right? And they're still doing it, evidently, right? But the Soviet Union and the United States never went to war. And they even in other places in the world, right, we never actually fought each other directly. We fought each other sometimes through proxies. But in 60 years or something like that, deterrence worked, right? It was expensive, and so forth. So my experience is that this control of the adverse dynamic behavior, which is accomplished through this thing I call the control structure, the design for reliability and all this kind of stuff, can have, as I said, 1,000 or 10,000x influence on performance. The stuff that people normally think about, I got a cool algorithm that's going to do this one critical part of the job, in my experience, has about a 5x impact on system performance. Right? So which would you rather spend your time concentrating on? If you think of it this way, I mean, you obviously have to do some of this, but you're a fool not to do this. It's not taught. And of course, therefore, most practitioners don't do it. So 85% failure rate. Now you see why. At least I'm convinced that that's why. Okay, so I draw this picture to kind of say it in black and white, right? Step one is to design the dynamic behavior you want, and everybody remembers to do that, right? You push the button, you do this algorithm, you do this, and then the sluice gate opens and the water goes down into the pipe, right? That's why we're building the system, right? But you got to do this too, and most people apparently forget to do it. And so that's what I found during all these years where I was the kind of the designated fix-it guy. I would go to the project and I was thinking they had pretty good requirements and they had a pretty good design for this. And they had nothing like a pretty good design for that. Now it manifested itself completely different ways, right? For the medical systems and for the military systems and for the police dispatch systems and stuff like that. But after a while, the brain, the mathematics trained brain begins to do some induction and generalize, right? And you come to a conclusion like this. So how do you do it? How do you do the right-hand side? So this is a lot of art, right? And it's probably not a one-size-fits-all answer, but I had the fortune of working with some really, really brilliant people who had some nascent ideas that were really relevant, and I was able to work with them and kind of take their ideas to a completed theory. You know most of these people, right? Walker and Bixler and Pete Blankenship and stuff like that. So what I decided is that there's an old method called FMEA, fault mitigation and error analysis, I think it is, right? It's been around for 70 years, right? And it's trying to write a list of all the ways your system could go wrong, right? And for most systems today, it's impossible. They're combinatorically too large, right? So you all have a laptop computer, right? And so how many lines of code are on your laptop computer? Probably a minimum of 400 million, because Windows by itself is 200 million without all the print drivers, which Microsoft doesn't build, right? So they don't count them. And Office is another 200 million lines of code. So before you're out the box, it's 400 million lines of software on that thing. There's no other human creation that has 400 million parts. Right? The Great Pyramid is 2.5 million blocks, but the dynamic interaction between the blocks is pretty simple, right? They just sit on top of each other. I mean, they have to fit nice, and they did a good job of that. But once they're there, the dynamic interaction is it's gravity, right? So we probably cannot. The method that is taught is this FMEA method, and it's probably worked fine when we were building systems that had a few thousand parts, right? I read somewhere, I can't vouch for it, but I read it, and it's a great thing, great story, so I cite it, right? That when the first Apollo rocket took off that actually went to the moon, there were about 100,000 parts, including all of the software. My mom worked on the guidance computer for that thing, right? It had, I think, 4,000 lines of software in it. Right, your wristwatch has 10 million lines of software in it, right? it's a different world. There's nothing in the world today that has 100,000 parts. BMW advertises that every BMW has 200 million lines of software. Most of it in the entertainment system, by the way, but because of design flaws that they have, you can kill the car by hacking the entertainment system, right? Anyway, so we can't do what the one method that we teach is, that is to actually find and think of in advance and find all the flaws. We need a stronger preventive strategy than a one-time correction, right? Okay, and so here's a strategy. What if we tried to completely separate the design of the algorithms from the design of the control structure? Completely separate, okay? And we could have, by the way, this is turned out to be kind of interesting. So on one system, I was the chief engineer for an air defense system. Turned out that the whole system was about 40 million lines of code. This was 30 years ago. That was a lot then, right? And the control structure thing I'm talking about was 10,000 lines of code. So you could actually do a lot of assessment on this control structure thing, right? But when there's 40 million lines of code, it's just kind of mathematically or unfeasible to do any kind of complete analysis, right? Especially since there were programmers in the early days of computer science, like Edward Dijkstra and Alan Kay, who, by the way, is still alive, but has been very ill, who said that programming should actually be a branch of mathematics and everything should be formally proven, right? But it was too hard for the average programmer, so nobody does it, right? And all the people who taught it are dead, except for Alan, well, Alan, by the way, is an interesting case. You can look him up. Everything about the personal computer worth doing, he and his little team at Xerox invented. I have a friend who says he invented everything about the laptop computer except the hinge, right? So the bitmap display, the mouse icon computer interface, object-oriented programming, the Ethernet, the laser printer, I can go on. All invented by one team mostly in the 70s. Alan's still alive, not well. A little story about Alan. So before we could build a real laptop computer, he had a wooden piece of wood with some fake keys and a fake little display on it, saying, we should try to build this thing. This was in the late 60s, early 70s. I met Alan when I was a 16-year-old kid. And he actually had this wooden thing and he showed it to me. First time I met him, he said, someday we're going to build this. And we all kind of rolled our eyes and said, how could we ever build such a thing? And so I have a friend it didn't have a hinge. So I have a friend who says he invented everything about the laptop computer except the hinge. Anyway, so it turned out that about the time I was starting to think about this, I ran into some people that were actually trying to do this for a completely different reason, to build a separation of the control structure. And so I just kind of said, hi guys, you're going to be my friends. And I built this system method around this great set of programming techniques that Walker and Dave Bixler and Chase Dane and all those people you know built. And it worked because the thing that implemented the control structure, even though it was fantastically complicated, was teeny. But the system could be as, the mission meat, as were all the algorithms that made the whatever do its actual mission, were gigantic, and that didn't matter, right? And so I called this thing the system architecture skeleton, and I'm going to talk about it a little bit. The people aspect here is very important. So the first program where I kind of said, I'm gonna try and make the team do it this way, was a 300-person project. That, by the way, was one of these programs that was in grievous trouble. They were 20% done and spent twice their planned original budget, and nothing was working, and everybody was frustrated, and the customer was angry, and was actually writing paperwork to cancel the program and stuff like that. And what I discovered is that I needed 3 people to build this architecture skeleton that implemented all of the dynamic behavior. With a 3-person team, you can staff it entirely with experts. You cannot staff a 300-person team with experts, right? On average, 300 people will be average. right? Law of large numbers, right? You guys get this, most audiences I talk to don't know what I'm talking about, but you get that, right? If you can enforce a separation, that is, you three people can actually build this control structure, and the other 297 people don't have to know anything about the control structure in order to do their work. And thanks to the brilliant work of this handful of people, they had, not intending it for this purpose, they had built something that met that test. And therefore I actually staffed the system architecture team on this project with some of the people who did the original creation of this thing. And we took this project that was dying and turned it into a huge success. And 30 years later, my former company is still the prime contractor in that system, and it's still being updated and used, which, you know, in terms of computer science systems, 30 years is like saying this is, you know, a steam engine or something, right? Because we figured out that how actually to isolate that bit of work to this small thing. What we were doing before is we were allowing the work of implementing the dynamic control structure to be implemented in small parts by every one of the 300 people. And most of them couldn't do it. It was too hard. By the way, we had the same problem with computer security when we started, right? Every programmer was responsible for computer security, and a flaw by any one of those 300 programmers would introduce a security flaw, right? And it wasn't until we started thinking about how can we enforce security policies. We can't do it as well for security yet as we can for this, but how do we enforce security policies so that they can be implemented by, so these guys actually figured out how to do all of the dynamic behavior sync, the dispatch, synchronization, rendezvous, all the stuff that causes computer science and systems to go crazy in this teeny little bit of software that only needed 3 people to look after. And then the 209 other 97 people didn't have to know anything about that, but could build their stuff, whether it's hardware or software. Okay. And that's the system architecture skeleton method. So that's the way I do it. Maybe some days somebody will think of a better way to do it, but that's, so we did this. There's some charts here I'll skip over that just talk about what it is, but you'll have the charts. Here's the propinquity part. I was by this time a pretty senior executive in this company. And so I could tell our projects, you have to do this. So I got to do what most theoreticians don't get to do. I got to run a 25-year controlled experiment where I forced 30 major programs to do this. Okay, and the bottom line is that they all were successes as compared to the 85% failure rate, right? And there's actually some formal analysis that says maybe that's not completely random chance, because it's always possible that even 30, a sample of 30 could be random chance, not much chance, but there's actually analysis. That, by the way, is what my PhD dissertation was about. I was able to force that, and the company was kind enough to give me all that data. So I came here at, age 50, while still working full time, and did my PhD and used this. This outcome is pretty different than the standard practice. So I think there's something in it. Someday somebody will do something better. But not so far as I know. If you want to learn about more detail, I got here, I did what academics do, I actually wrote a textbook. And it has pictures like that in it. One last topic. So the hot word on the street now is artificial intelligence, right? And all of its variants, machine learning, deep neural networks, large language models, all those things, right? Interesting subject about which we can say a lot. I have a friend who's at Scripps who I'm told is one of the world's foremost experts on the human brain. Okay, I'm not a biologist, so I can't really judge, but lots of people who I respect say, he really is the guy. And what he tells me is that every year through imaging and stuff like that, we learn more and more about the mechanical structure of the brain. And our knowledge about of what we think we know about how it operates goes backwards. Because everything that we thought about the brain has turned out to be wrong. We thought things were stored in one location, just like in a computer, and apparently it's not true. We thought that particular locations in the brain were very specialized in function and storage, and apparently that's not true either. So all the stuff about lobes of the brain doing this, I mean, because the brain, if it's damaged, it can reprogram itself, and people who lost that lobe can reclaim that function, right? And he says we know nothing about the processes and methods, what we would call algorithms. Okay, this is the world's foremost expert on the brain. And so I explained to him how computers work. He says, I don't know everything about how the brain works, but it ain't like that. It ain't like that. You know, my wife's phone number is stored in a particular identifiable place in here, right? But not in here. Okay. So whatever all these algorithms are doing, and they're very clever, fine pieces of work, right? They are not doing what the brain does. They are not mimicking the processes of the brain. Now, our brain has 1 million years of evolution designed to achieve a certain amount of efficiency and to prevent certain kinds of errors, right? So if we were mimicking the processes in the brain, we might inherit some of that into our AI, but that's not what we're doing. The processes we are using, as I said, are clever, but they're not, according to my friend, they're not at all what the brain does. And there's actually a whole different lecture I give sometimes that cites a lot of theoretical work that it cannot be what the brain does. I'll leave that provocative thought with you, and if we have time for questions, we can talk about that. So there's no bound on the errors that these things can make. And I'll tell you something interesting. You know, I used to be the CTO of a big company, so I knew my counterparts. And so I still know the people at Google and Meta and Microsoft and stuff who build this stuff. And I talk to them, and they fall into exactly the pattern I described on that oval, right? They do the stuff on the left-hand side, and they spend no time at all on the stuff on the right side. That is, they designed to get the behavior they want, but they do really nothing to protect against errors. What do they say? They say we put so much data into it, it will train itself out. Well, first of all, it's a completely unproven conclusion, right? Not to mention the data they train on is usually the entire internet, which, pardon me, is not completely full of correct data, all right? But even if it was full of correct data, and by the way, the Google people get points in my book because they actually try to curate the data. The ChatGPT people proudly say they trained against the whole internet, which I think is admitting to a flaw, right? The Google people say we curated what we trained it against, which I think is at least trying to do something. But there's no theoretical basis for saying that that will prevent bad behavior. And we all know this stuff makes mistakes, right? Or at least if you played with it, you know it makes mistakes. It makes up citations. It states facts that are completely contrary. Perhaps it needs to be something as simple as having it the ability to say, you know, I don't know the answer. I don't have enough information to give you an answer, but apparently it doesn't do that either. It always gives you an answer. There are stories, and I can't vouch for their truthfulness, of where some lawyer who didn't have time had ChatGPT write a legal brief, and it just made up citations, fake cases, fake case numbers, and the judge caught him, and he was debarred. Now, whether he actually used ChatGPT or only said that afterwards so that he would try to not get debarred, I can't tell you. But I myself have done experiments, and I can tell you it makes a lot of mistakes. Anyway, so my wife, PhD in linguistics, right, is the one who I cited before saying, you know, computer language is what's so hard, 40 verbs, 100% regular grammar. I was at a party when about 2 weeks after ChatGPT came out, a birthday party for a friend of mine who was brilliant in The other 12 people in the room were brilliant too. And one of them said, but I was being skeptical about whether it could do anything useful. He said, but Neil, it can write software code. I hadn't thought of that. So give this person, by the way, was a famous actor. So, people can be smart and knowledgeable in lots of ways, sometimes unexpected, for an insight that I had not thought of. And then, I applied my wife's rule, 40 verbs, 100% regular. It's obvious that it should be able to write syntactically and lexically sound software code. That doesn't mean it's any good, right? Because writing good software code is Dr. Dijkstra and Dr. K said 40 years ago, as I cited a half hour ago, right? That writing good software is a lot more than just writing syntactically correct statements, right? And I would express it saying, you got to do the right-hand side of my oval and not just the left-hand side of my oval, right? And so if you just use AI to write code, by the way, the world is full of tools, IBM and Google, and everybody has tools, probably some of you use them, right? That are specifically tailored to help you write software code. And it's going to be a revolution. It's going to create code a lot faster. It's going to create bad code a lot faster, right? Of course, humans create a lot of bad code too, perhaps. The error rate, of course, is complete, but it won't fix any of the problems that I talked about here, right? So there is interesting work going on. Even some by a friend of mine named Doug Rosenberg, who's looking at how can you train large language models to specifically learn useful things about software development tasks, how to write specification, how to do design cases, how to do testing, how to do integration. People are actually training large language models to do these specific kind of tasks, which turn out they do a little better, but it won't fix any of this problem. So I'm not aware of anybody trying to, as it were, do the software architecture skeleton in one of these AI tools. And so I'm actually talking to some of my buddies who are the original developers of the stuff, said, but maybe we should do this. Anyway, so what I said, so engineered systems are really vital to society. They got us from 30 years to 70 years, and that's a good thing if you're aspire to live longer than 35 years, right? Most of us do. The efforts apparently to create them mostly fail. Maybe it's not as bad as the 85% this one source cites, but nobody cites a number smaller than 60 or 65%, right? The reasons described in the literature are about what they call requirements creep. You could find probably 100,000 references on the internet to that term, right? And all I got to tell you is I spent years being the fix-it guy, and that was never a problem. Never. Okay? What I saw was design flaws, and I saw the same design flaw over and over again. It took me a while to notice that. We came up with a solution that, as I said, because of my authority in the company, I got to impose on a bunch of projects. And so I got a lot of interesting test data, and it seemed to work. And then I said a few things about AI and large language models. So that's my story for the day. There's a paper coming out from what people say CSER, the Conference on Systems Engineering Research. Is actually going to be published. Well, the conference is later this month. I don't know when the paper will be published, probably later this year. That says all of this in the same words, but at greater length. And in my textbook, the one I had a picture of, it says it at still greater length. So if you're interested, the details are there. And I'd be glad to take any questions or any argument.
Going back to the left-hand side and right-hand side, do you think there's going to be another right-hand side in the future?
Another
right-hand side, a further right?
Yeah. Somebody will come up with maybe a whole another phenomenon. And I certainly believe that people come up with a better way, or at least a different way, to correct it other than my system architecture skeleton, right? We all kind of work in successive approximations, right? So, sir.
How could you, so how does one go about testing a project when either a successful test or a failure of a test could have catastrophic consequences?
Yeah, so it's a great question. And the thing that most people don't realize is that we spend unbelievable amounts of money testing our systems. I worked on a major air defense system once that was designed to protect against the possibility that the Soviet Air Force would fly into Western Europe. And it was designed therefore to be able to detect and deal with up to 200 high performance Soviet aircraft in the sky in this little area at once, right? Well, I didn't have 200 Soviet aircraft and trained pilots, right? And I, and I can't hire the US Air Force even to come out with 200, it's just too expensive, right? So we had to build a simulator that would simulate what our radars would see if there were 200 Soviet aircraft in the sky, by the way, a bunch of friendly aircraft too, right? And then we had to convince the customers that our simulator was okay. We spent more money building that than we built the air defense system, right? That's not unusual. These things are really hard to test if you're doing the test right? The test program for a submarine or the Minuteman missile. These are big, expensive things that take years. And more importantly, take years and years of planning. Because you usually have to build something like the simulator that, like I said, could be as expensive to build as the product. Great question, though. Good insight. There was another question, sir.
One of the premises of the control system that you pointed out was that when the original system is very, very big, the control system is much smaller, so it's easier to analyze its failures. Are there any situations you know of or anticipate where the system is so large that the control system is still very big and needs another control system or something like that?
Could be. I mean, the fact of the matter is systems today are large beyond what we could have imagined even in 1980, right? I can remember when a program that had 1 million lines of software code was considered too large to be feasible, right? I'm that old, right? And of course, that's nothing today, right? And hundreds of millions of lines of code is pretty popular. So the thing I talked about, the control system did not grow linearly with the size of the application, right? That was its salvation. Is there no circumstance where it wouldn't become unwieldy? I don't know. All I can say is in these 30 or so real programs, it never became unwieldy. Actually, in fact, we built 2 versions of this control system, one for Digital Equipment Corporation computers and one for everything else. And we built all 30 of those systems with those same, literally the same code base for the control system. So, but it's a great insight. And I only built and tested a certain range of societal systems, and there could be others for which this strategy wouldn't work. And then some smart person will come along, I'm sure, and create a better one. Something else, ma'am?
It seems like, so the premise of half of your oval was that you should design for things that you don't want to happen, but it seems like sometimes those side effects might be unknown until they do happen.
Yeah. Okay, so the answer is you got to read the slides I skipped over where I described how we actually do it. Because what we do is we since the control system is so small, I can build it much quicker than I can build 100 million lines of application code. And so if I've got a 7-year program, pretty typical for a big engineering project, I can have that up and running by month 6. And I have 6.5 years to exercise it and see all the problems I didn't anticipate and fix them. Rather than what happens now is I don't see them till I have all the parts of the system together and I'm in the last 6 months of my 7-year system and I don't have time to find and fix them all. And they're hard to find because there's 500 million lines of application code muddying the waters. Right? So if you read the charts I skipped over, I try to address it. That is a great question, good insight. You're thinking. Sure.
So in the beginning, we'll emphasize instead of understanding each part, it's important to understand the whole system. So it's kind of from local to global. But later, when you talk about separation of the functionality and the design, you use the example, say, allocate a specific task to a small team. So it's kind of from global to local. Could you elaborate more on that? And especially, how important is that a small team to understand the whole picture or say the...
Yeah, so the premise, right, and like I said, you could read the slides I skipped over or get my textbook and read chapter 4, which is more than 100 pages. So it tries to deal with this in some detail, is that the control structure can be completely encapsulated in this fairly small thing. And you can then, instead of do what most people still do now is try to simulate the control structure. Well, your simulation won't produce all the types of adverse behavior that you'll see in the real system. But if you build the real control structure, and then I have a strategy for how you populate it with something in advance of the real software and real hardware showing up, so that you actually execute it, you don't simulate it, and therefore, in principle, all the weird behavior, the queuing, the turbulence, the message lack of synchronization, right, deadlocks, race conditions, there's this whole vocabulary in computer science, right, that describes all these odd things, bad things, right? It will happen, and you can see it, but there's only 10,000 lines of code there, and so it's easy to figure it out, where it's really hard to figure it out when it's in the midst of 500 million lines of code, and you have 6.5 years and not just 6 months, right? So there's no magic when you see the anomalous behavior. You have to dig in and trace it to its root cause and find and fix it, and that's hard, but it's easier if there's only 10 or 20,000 lines of code there than if you have millions. So that's kind of an area that's left unplumbed, right? And that's where the art that I made reference to earlier on comes in. But thus far, at least for the class of systems that I was involved in, it's ignored. There are probably systems out there for which it wouldn't. Right?
I was wondering, so you mentioned you've had 30 projects to test this framework and throw it at people. I imagine that on some of those projects, you've had some of the same people come in and work on some of these, like multiple of these projects with this framework that you have. And perhaps some of those same folks have also worked on projects outside of that framework, previously or in different settings simultaneously or what have you. What have they said? What have people remarked about the system? What has been their experience?
So there were all kinds, with that many examples, there were all kinds of bizarre things. So we had programs that started without this, that we retrofitted this into. We had programs that started new with this. We had, as you alluded to correctly, we had projects where this was done by the original developers of this method. But interestingly, we had other projects where we had other people who had to learn it and then were able to go. That's a big thing, right? When somebody other than the inventor can replicate the work, right? We did that. And we even had a couple of projects, this seems crazy, that started with it and then abandoned it because the customer lost interest or whatever. The project, as you would expect, went crazy. And the performance and the schedule and the cost and all that stuff going haywire. And on one of these projects, we actually put it back in and the project got back on keel. So we had, with 30 samples, we had a range of interesting outcomes. I mean, it's probably not, 30 is not a gigantic number, but when each of these things costs a couple $100 million, it's a pretty good set.
Aaron, did you have a question?
Mine was kind of tied to the question there.
Okay.
Yeah.
So we have wine and cheese next door. Let's assemble next door. Many thanks for a very stimulating lecture.
Thanks a lot.
Thanks.
Brought back a lot of good memories.
Nice.
Yeah, Peter and Dave and Jason and Water.
I think Dave's still working there.
Dave retired.
He finally retired.
But
Just recently.
I'm just recently, I'm literally talking to him.
Yeah, we should throw out the Siegel
Yes, Dave.
Right before I
It's not as trivial as I thought it was going to be in terms of how we pay. The university